We will take some time this week to review some modeling techniques in regression. Most of this will be done using matrices for multiple linear regression. This should be review. Let's start out with an example. This is an example of a study done by a researcher to see if viscosity can be predicted from catalyst feed rate and/or temperature. We will use this example to show the techniques throughout the lecture. There are many situations where you have an output or response variable that you would like to predict based on one or more input variables. These input variables can be quantitative or qualitative. We would like to explore this relationship and create a model that represents it. We will do this using a mathematical equation. The type of equation that we will use will be a low-order polynomial. For one input variable, the basic model is given in the slide. The response in this case is y, the parameters are the betas, the input variable is x, and the error terms are the epsilons. The beta subj represent the change in the response for a one-unit change in variable j, holding the remaining predictor variables constant. Beta sub 0 represents the intercept terms. This model represents a hyperplane in the k-dimensional space of the predictor variables. If k equals 1, then it represents a line where we consider the beta sub the slope of the line. In this case, the sign of the slope will indicate whether the relationship is increasing or decreasing as you increase x, and the strength of the relationship is based on the steepness of the line. Beta sub 0 represents the point where the line crosses the y-axis. For the single x variable case, we can use basic techniques for estimating parameters. These would be determining the slope from rise over run, then determining the intercept based on that number and some xy values. But what do we do when it is more complicated than that? When k greater than 1, we end up more complicated models than we talked about on the previous slide. We could also have other terms in the model beyond main effects, such as two-way interactions. How would we create those models? On the slide is a model with k equals 2 and the two-way interaction term. We can still write this in terms of a linear model. We will do this by replacing x1, x2 with x3. This shows you that as long as the model is linear in its parameters, we can write it in terms of a linear model. Now, what about a higher order model? The equation for a full second-order model is given on the slide. Notice that we have not only the interaction terms, but we also have squared terms. We can see again that this can be written as a linear model based on the equation at the bottom of the slide. We show this so that you can see that as long as the equation is linear in terms of the parameters, we can use regression to estimate the parameters. Now, for these more complex situations, how indeed do we estimate parameters? In order to estimate the betas, we will use the method of least squares. Recall that we have been assuming that the error terms have constant variance and are independent. We will estimate the parameters by taking the sum of the squared error terms. Notice that based on the relationship, this is just taking our equation and summing the square of it over all observations. Now we will take the derivative of L with respect to the betas, set it equal to 0 and solve those equations for the betas. We call these the least squares estimates for our parameters. Now, with the number of potential betas we could have to deal with, it is much easier to do this in terms of matrices. The equation for our model is given in the slide. For this equation, y is a vector of response values, x is a matrix of input values, beta is a vector of parameter values, and epsilon is a matrix of error values. So now, how do we get our parameter estimates? The equation on the screen gives you the estimates for the betas. Most statistical computer packages will output these for you. Now that we have the parameter values, we need to get the fitted values and residuals. Recall that the fitted values are the set of responses that you get for a given set of input values based on the model. We refer to them as the y-hats. We can find these values by plugging the x values into the equation and solving for y. The equation for determining the fitted values is in the slide in both matrix and scalar form. You should also recall that a residual is just the observed response for a set of x values minus the fitted response for those same x values. That equation is given as well in the slide in both scalar and matrix form. Now that we have the residuals, let's look at how you estimate the variance. Recall from our discussion about ANOVA that the estimate for the variance is the MSE, which is given as the SSE/DFE. This idea also works for regression modeling. Now let's look at an example. Here is the expected value and the variance-covariance matrix for the beta hat vector. Notice that this is unbiased. We know that we can use hypothesis tests or confidence intervals to decide whether or not certain terms and/or variables are needed in the model. We can do the same thing based off of the results from a regression. Notice that up to this point, we have not stated what distribution the error terms follow. To use the typical hypothesis tests, we require that the errors follow a normal distribution or NIID 0, 2. Notice that these are the typical error assumptions that we have been using all along. First, we need to test to see if any model beyond the horizontal line model is needed. To test whether or not we even have a linear relationship, we will run a test for overall significance. The null and alternative hypothesis for this test are given in the slide. Notice that this is testing to see if any other beta is needed beyond the intercept term. This is similar to the one-way ANOVA test. If you reject this test, then there is at least one x variable that is needed in the model. So how do we test this? We will do this using an f-test. The test statistic is given on the slide. Recall that in this case k is the number of input variables. Then on the bottom of the slide is how you determine the p-value. Let's look at an example. We will create individual hypothesis tests for the betas based on the null and alternative hypotheses given on the slide. Based on this, we will remove a term if we fail to reject the null hypothesis. So how do we build the test statistic for these hypotheses? Because of our assumptions on the error terms, we can use the t-distribution to build our test statistics in this case. The test statistic for each of the parameter hypothesis tests is given in the slide. For the -1/+1 coding, the variance in this case is sigma sq/n. Most statistical packages will create these tests for you. Let's look at an example. Let's go back to the viscosity data and create an analysis. On the slide, I have highlighted some of the important items. First, the overall f-test from the ANOVA is significant. This tells us that at least one beta other than beta 0 is not equal to 0. Now we can get an idea about terms needed in the model based on the p-values for the t-tests. Of course, remember that to be able to use these t-tests to make decisions, the model matrix needs to be orthogonal. Since it is not, we should be just using this as what I would call a first look. Based on that, it would seem that both may be needed. Now you should also see that I have highlighted the model itself. This equation can and will be used to predict the viscosity at given levels of the temp and feed rate. Recall that these predictions are just estimates. We will need to put some confidence with those estimates. We will do this using confidence intervals. Let's first talk about these intervals for the parameter estimates. Since the errors come from a normal distribution, we can also use the t-distribution to build confidence intervals for the parameter estimates as we did to build hypothesis tests. The equation for a confidence interval for an individual parameter is given in the slide. Let's go back to the viscosity example. Here is the construction of the confidence interval for the estimate for the parameter for the feed rate. This can be done for each parameter estimate. Now, what do we do if we want to put some confidence around our estimate of the response? We can create confidence intervals for the mean response and a future observation. We will use the same estimate in both cases. This estimate will come from substituting into the equation a point in x space that we are interested in estimating the response for. This estimate is given in the slide as y hat of sub 0. The only differ for NCE when we create the intervals will be the variance estimate. The confidence interval for both the mean response and a future observation are both given in the slide. Notice that the variances are different. For a future observation, the variance includes the variance of y and the variance of the mean. Now, how would this change if we wanted to create confidence intervals for a whole set of possible x values? In this case, we would create a confidence band around the entire set of values. Notice that we use the critical value based on the Sheff method. This allows us to cover the entire band at alpha equals 0.05. If we had used the t-value and created each interval separately, then the overall alpha would be much larger than 0.05. So now let's say we wanted to create prediction bands. The only change would be that we would use the variance estimate for the future response instead of the mean response. Now let's go back to the viscosity example. Let's use this example to create 90% confidence and prediction intervals for the values of our inputs given on the slides. Here are the values for the intervals. Whether these intervals are too wide to be useful is really going to be based on your knowledge of the process. You should also notice that the prediction intervals are wider than the confidence intervals. This is because the variance for the prediction intervals will always be larger since it includes the variance for the observation as well as for the mean. Recall that RSQ is the amount of the variation in the response explained by the model. We can find RSQ based on the equation in the slide. You should realize that a large RSQ doesn't necessarily imply that the model is a good one. This is because the more terms we add to the model, the higher RSQ becomes, even if we don't need those terms. We need to adjust for this. We will create a measure called adjusted RSQ. This measure penalizes the model for including unnecessary predictors. The equation for RSQ adjusted is given in the slide. We usually determine that a model has more X variables than necessary if the difference between RSQ and RSQ adjusted at least 10%. Again, most computer packages will present these summary measures as well. Let's do an example. Another indicator of as good model is one that is not highly affected by individual observations. We can check for this by calculating RSQ for prediction. RSQ for prediction is found based on the equation on the slide. We first need to calculate the press statistic. The press statistic is calculated by summing the squares of the deleted residuals. A deleted residual is found by using the equation in the slide. Now let's determine the three different RSQ values for the viscosity example and interpret them. Here is the output again. You can see that RSQ and RSQ ADJ are quite close. This means that we probably don't have extra terms in the model that we don't need. Also, these values are quite high, which means a large portion of the variability in the viscosity is explained. We can also see that the RSQ pred is also high. This means that there are very few, if any, points that are influencing model any more than any others. Recall that for linear regression, we usually assume that our errors are independent and identically distributed normal with constant variance. We will use the residuals to test these assumptions. You should note here that in most situations that we will deal with in this course, the independence assumption will not be met. We will accomplish this by viewing residual plots. Residual plots are plots of the residuals versus an important characteristics such as time, predictors, fits, etc. These plots should show no noticeable pattern. In fact, we should be plotting the studentized residuals instead of the raw residuals. This allows us to easily assess outliers. You should be cautious of concluding that there is a pattern on a residual plot with a small number of points. We have other diagnostic measures that we can use to assess the validity of a model. In this class, we will use the Durbin-Watson test more often since it tests for autocorrelation in the residuals. Now let's go back to the viscosity example and assess the assumptions. Based on these plots, the assumptions seem to be met. Let's check the residuals versus feed rate. The residual assumptions seem to be met based on this plot as well. What if any of the assumptions were not met? If any of the assumptions are not met, the techniques on the slide could be used to try to remedy the situation. Up to this point, we have been looking at an example with very few predictors. Things become more complicated when the number of predictors gets somewhat large. Here we will have to deal with model selection procedures.